Well, here we go again. This is another installment of the videos for sequence and series. We have a couple more tests today. Let's see if we get this started. Okay, we have a couple more tests today. We've already talked about three of the tests. I wonder if you remember those three tests. We had the nth term test, which remember will only test for divergence. If the limit does not equal 0, then we know that the series diverges. We did the geometric, which is probably my favorite because it just seems very straightforward. And remember, on the geometric, you can go ahead and find the sum. We had that formula for the sum. And then we had the telescoping, which I think I mentioned is a little less common than the other ones. But again, if you can factor the denominator, it's likely that it could turn into a telescoping, and then a telescoping will always converge. In order to find the sum, you have to kind of write out the terms and watch for the pattern. Okay, so we have two more tests, the integral test and the p-series test. Um, so the integral test is one that it would work well on terms that are easily integrated, obviously, because we're going to do some integration. There's a couple conditions for this test. Your series has to be positive, meaning all the values are going to be positive. It has to be continuous, so there can't be any breaks or holes in the graph of the function. And then it has to be decreasing, which hopefully it makes sense because if the function's decreasing, that means the terms are getting smaller and smaller. So the values that you're adding, right, because a series means you're adding in terms, so the values that you're adding hopefully are getting closer and closer to 0. The question is, are they getting closer to 0 fast enough? Okay, so those are the conditions. So here's the idea. You take what was the series term, the a sub n, and you think of it as a function. Um, so we're going to look at the integral of an f of x, right? Because we integrate in terms of x. So here's the thing. Either they both converge or they both diverge, meaning if the integral equals a constant. Remember, we've done these unbounded integrals before, right, where you go to infinity. So if the integral equals a constant, then that means that not only does the integral converge, but the series converges. And then if the integral equals infinity, so in other words, the integral doesn't exist, then that means that the series is going to diverge. Okay, one thing to keep in mind is just because the integral converges to a specific value c, that does not mean that the series converges to c. So just because, say, the integral equals 2, that doesn't mean that the sum of the series comes out to be 2. Okay, so let's look at this first example. When I look at this, I'm thinking actually if I did the nth term test, right, the limit as n approaches infinity, and I did the horizontal asymptote rules, wouldn't this come out to equal 0? And remember, that's inconclusive for the nth term test. Okay, so that's why I can't use the nth term test. It's inconclusive. So this would be a good candidate to use the integral test, because I can look at that and tell that that's going to integrate not too bad either. So I have to do a quick check. Is it positive? Well, if you're only going from 1 to infinity, then the n is a positive term. N squared is always positive. Is it continuous? Yes, there's no breaks in the graph. Notice the denominator is never going to be 0. And then is this decreasing? Well, do you see how the denominator is increasing a lot faster than the numerator? That means the denominator is getting really, really big. Yeah, the numerator is getting bigger, but it's not getting bigger as fast as the denominator. So the terms are going to be getting smaller, right? Because if the denominator is getting big, the overall value of the term is getting smaller. Okay, so I won't spend too much time, discussing those anymore. I just wanted to point that out. So if I set up an integral, just kind of looking at it, and remember I'm writing it as x instead of n. Well, hopefully you can notice that if it's x over x squared plus 1, that's like a u prime over u. We're going to have to manipulate it into place, right? So I kind of want to put a 2 in there, which means I put the 1/2 out in front. Great, so when I integrate u prime over u, I'm going to get the natural log. So here's my integration. I still have to evaluate it from 1 to infinity. And all I didn't like take it all the way out, because if I plug in infinity and I'm taking the log of infinity, doesn't that equal infinity? Of course it does. So this integral equals infinity, which means the integral diverges, so therefore our series diverges. Okay? Look at the next one. Yes, you technically have to ask, is it positive, continuous, and decreasing? And it is. So let's look at the integral of this one. This one's kind of interesting. Is it a u prime over u? No, no. So how am I going to integrate this? I'm wondering if anybody is noticing our old friend. If it's a 1 over x squared plus 1, isn't that arctangent? Oh, yeah, okay, arctangent. So we plug in infinity, right? We plug in 1. So arctangent of infinity. In other words, when is the tangent function going to infinity? Well, isn't the asymptote at pi over 2? Okay, what about arctangent of 1? When does tangent equal 1? Remember your unit circle and remember your chart? That's going to be pi over 4. So this integral comes out to equal pi over 4. So it equals a specific constant. That means not only does the integral converge, but also the series converges. Okay, then we have, so that's the integral test. So now we have the p-series. The p-series test is probably one of the most straightforward, and in a little bit, this p-series is kind of break everything wide open. Towards the end of this video, I'm going to kind of show you my common sense method, which the more we do it, the more we practice it, I think it's one of those where you can just, it's the kind of thing where you can look at a series and just kind of automatically know converge or diverge. Now, granted, the AP exam is going to want you to identify some of the different tests, so we're still going to talk about tests, but everything in you is going to want to look at it and just say, oh, I know the answer to this one. Okay, so the p-series is this. If you have 1 over n to some power, p for power, so it might be a 1 over n squared, a 1 over n cubed, a 1 over n to the 5th, 1 over n to the 1/2, okay? So these are basic looking, 1 over n to some power, some polynomial. Then here's the idea. If that p is greater than 1, so if it's like a 1 over n squared, a 1 over n cubed, a 1 over n to the 4th, then automatically we know the series converges. The series converges. But if p is between 0 and 1, and notice we have to say we want p to be positive, because otherwise this wouldn't be a 1 over, right? If p is a negative exponent, then wouldn't that just move it to the top? Okay, and then it's not a p-series anymore. Okay, so if p is between 0 and 1, so if it's a fraction, or if it equals 1, notice the equals 1. So if this is 1 over n, we're talking this situation. If it's 1 over n to the 1/2, 1 over n to the 2/3. All right, so if the p is a fraction, or if the p is 1, then we know that the series diverges. And in fact, this p equals 1 is a special series. It's called the harmonic series. I don't know that you have to know that by name, but we will use that term. So 1 over n is like our harmonic series. And we know it diverges, right? Because then the p would be 1. We know it's a diverge, but this 1 over n is kind of our middle ground. It's kind of that line that we draw in the sand between diverge and converge. Okay, and hopefully I can kind of gradually explain that. So like I said, the sum from 1 over n of the harmonic, we said, is a diverge. And if we want, we could prove that by the integral test, right? If you integrate 1 over x, doesn't that equal natural log of x? And then if you plug in your infinity and your 1, that's going to come out to equal infinity. Okay, so we've just kind of proven that this 1 over n, we've proven it by the integral test. And so you could have used the integral test on this, but you didn't have to, because now we know the p-series, right? And this is like a 1 over n to the 1st. Now, something that I want you to think about, notice this next example, it's 1 over 2n plus 3. So it's not 1 over n, okay, but it's essentially 1 over n, right? The power of n is still a 1. And so we're going to kind of call this the general harmonic. And it still is a diverge. It doesn't matter if you multiply n by 2 or 10 or 100. It doesn't matter. If you add 1 or 2 or 3, it doesn't matter. It's still, as far as how fast this function is decreasing, it's very similar. Okay, so it's still a diverge. So with that in mind, these are pretty straightforward. If I have 1 over the square root of n, well, that's a p-series, right? Because isn't it n to the 1/2? All right, and if the exponent is less than 1, boom, we know it's a diverge. What about the next one? Is it a p-series? It doesn't look like it at first, but couldn't you combine the n to the 1st and the n to the 1/2? Isn't that just 1 over n to the 3/2? All right, there we go. And the p, the exponent, is greater than 1, so it's a converge. That's what's so great about p-series. There's no real work to do. You don't have to integrate anything. You just have to look at it and identify the exponent. All right? Look at this one. It's not a p-series, right? If we're just 1 over n, great, it's a p-series. It's not a p-series. And I'm thinking about, compare this to 1 over n squared. Well, 1 over n squared is going to be decreasing faster than 1 over n. Well, n times natural log of n is not quite as powerful as n squared, right? Because natural log of n, if you compare the graph of natural log of n to just the graph of n, it flattens off a little bit sooner. So how am I going to evaluate this one? Well, let's do the integral. On this type, remember we said if you're integrating and there's a log, don't we always let u be the log? And then, of course, du is 1 over x. So if we solve for dx, let's see, that's going to be x times du, right? And so now if I rewrite my integral, I'm going to have just 1 over u, right? Because isn't this x going to cancel out the x that was in the denominator? All right, and if we integrate that, we're going to get the natural log of u. And so now we need to substitute back in, right? The u was actually a natural log of x. So now if I evaluate my 1 to infinity, again, I'm going to kind of shorten this, because if I plug in infinity, I get natural log of infinity is infinity, and then the natural log of that is still infinity. So in this case, not only does the integral diverge, but also the series diverges. So think about this. This 1 over n was a diverge. 1 over n times natural log, which means the denominator is increasing a little bit faster than n. It's still a diverge. But if this were a 1 over n squared, we know by the p-series that it would be a converge. So there's kind of this fine line between n and n squared. Okay, here's the kind of thing that we're going to gradually develop. Okay, this is I call it Napier's not very technical common sense approach. So here's what we're thinking about. Yes, I want my terms to decrease to 0. But I need to figure out how fast they're decreasing to 0. So basically, I need to kind of compare how fast the numerator is decreasing compared to how fast the denominator is decreasing. Okay, so look at the first one. We already know, hey, that's a p-series. It's a diverge, right? What about this one? Well, this is the one that we just did, right? So compare how fast the numerator is increasing. They're both 1. And do you see that this denominator is increasing just a little bit faster than n? But we already said, hey, that's a diverge. So let's go backwards. 1 over natural log of n. Well, I could, let's see, did I do this one? No. I could do a, actually, I think I could do an nth term test on this one. No, that would be 0. Maybe I could do an integral test, except I think I might have to do integration by parts. I'm not sure. Anyway, what I want you to do is compare how fast the numerator is decreasing to how fast the denominator is decreasing. Well, do you see that the difference in the 1 over n is a bigger difference in how fast numerator and denominator decrease than this one? So this one's going to 0, but it's going to 0 a lot slower than this one. Well, if it's slower than this one, and this is kind of my standard, really I guess these two are kind of my standard, then doesn't it also have to be a diverge, right? It's decreasing slower than the 1 over n. Well, what about 1 over 2 to the n? Well, you could say it's geometric, right? You could think of it as 1/2 to the n, and so therefore we know it's a converge. But again, compare how fast the numerator is decreasing, or I should say increasing, compared to how fast the denominator is increasing. Isn't 1 over an exponential, isn't that a bigger difference in how fast they increase than, say, 1 over n? What about 1 over n squared? Well, we already talked about that's a p-series, right? And so that's a converge. But again, 1 over n squared, there's a bigger difference in numerator and denominator than there was in, say, 1 over n or 1 over n natural log of n. So do you see how we're kind of comparing everything to this 1 over n? Now, in order to talk about how fast things increase, we need to just kind of take a step back and talk about just different basic functions. All right, so consider all these different kinds of functions separately. Consider them separately. I want us to put them in order according to how fast they increase. right? I mean, if you think about the graph of n, right, it's linear. If you think about the graph of square root of n, it does this kind of thing. Well, it kind of starts to level off, right? So it increases slower than n. So let's do this. Let's talk about the fastest. Which of them increases the fastest? Well, we talked about the other day, even though we're not as familiar with it, that n factorial increases faster than anything else. Period. Okay? So that's definitely going to be the fastest. Um, but let's think about this. If we compare the graph of the square root, I'm trying to move this thing out of our way. Can I? Here we go. If we compare the graph of the square root of x, which is the blue one, and let's compare that to the red one, which is the natural log. Which one increases slower? Well, hopefully you can tell that the red one, the natural log, increases slower. Okay, so the slowest one that we have up here is natural log of n, and then right after that would be the square root of n. Okay, so now what would be next? Well, after square root of n would be n, because you're thinking like n to the 1/2 compared to n. And then which one would be next? Well, n squared definitely increases faster than n, right? N squared will be like a parabola. N is just linear. Parabolas increase faster. So now we're down to e to the n and 2 to the n. Well, they're both exponential. Which one increases faster and which one increases slower? Why do you think I would say 2 to the n increases slower than e to the n? Well, what does e equal? Doesn't e equal 2.7? So wouldn't 2 to the n increase slower than 2.7 to the n, or 3 to the n, or 4 to the n, or something like that? So e to the n is just slightly faster than 2 to the n. Okay, so that means these are the ones I'm kind of looking at on the denominator. Compared to the numerator. So let's see if we can put it all together. And this one is really a stretch. We're going to talk more about this next time. But this one is really a stretch. So what if I want to talk about this series? That's not one that we had a test for yet. If I did the nth term test, I would have infinity over infinity. I would have to do L'Hopital, and if I do L'Hopital, it's going to come out to equal 0. But remember, nth term test is inconclusive if the limit equals 0. And it's not geometric. Is this one that maybe I could integrate? Well, we have talked about integrating 2 to the x, I think. But I don't know how I'm going to handle that x. So this doesn't fit any of the ones we've done so far. But let's use my not so common sense approach. Let's compare. I know the top is not a 1, but let's compare how fast a linear function increases to how fast an exponential increases. Well, isn't that a lot different than, let's say, for example, how fast 1 increases compared to how fast n? So if I have a constant of 1 and I compare that to the linear y equals x graph, I'm thinking about the difference in how fast they increase. Well, think about the difference here. If I have a linear y equals x graph and I compare that to an exponential that almost kind of shoots straight up, doesn't the 2 to the n increase a lot faster than n? And because it's a lot faster and it's falling over here in this category, I can kind of look at it and say, yeah, that's got to be a converge. Okay, now I want you to kind of be thinking through this, but as you're going through the homework, make sure you're still applying the tests as well. Okay, so these problems are your homework, and I hope they won't be too bad. So good luck with those, and we'll talk again next time.